So hi everyone to today's lecture. Today we are going to continue to talk a bit about the multi-object synchronization, chapter 6 in the book, and then we will talk quite a bit about the scheduling. Before I start, there will be extensions for assignment 2 since I failed miserably to give you the lectures early on. So assignment 2, I will post the new date and send an email. Last time we were talking about how multi-threaded applications and multi-object threading can negatively affect the performance. We talked about a few ways to basically, if you have a lot of threads trying to access the same object, to reduce the lock contention by fine-grained locking, where you would basically divide for example, hash table into buckets and have a lock per bucket. That's one solution. We talked also about the pair processor data structure, where you would basically use the pair processor heap to put in the data to load the data that you plan to process, divided into different parts again. We also talked about the ownership slash staged architecture, where you would only have one thread at a time accessing the shared data, by, for example, keeping the data in some sort of linked list or a queue or something, and once a thread gets access to the data, it removes the data from this shared data structure, and then no other thread can actually load it. We also talked a bit about the MCS locks, and we said that they are spin locks that are basically implemented such that to optimize to optimize for when the lock is contended. So it's an implementation that basically tries to optimize for the case when the lock is mostly busy versus most other implementations which would optimize for when the lock is free. There's the RCU read copy update implementation, where you basically have more of a stronger guarantees on when running with writing, when the thread is writing, versus if you're running to read. So threads that are reading the data have more relaxed guarantees. And both of them, we said, rely on atomic read, modify, write instructions. And last lectures, I felt that it was turning a lot into this and that and read and write, and I think I saw that many people were confused, so I hope this helps a bit. So the MCS locks and the RCU locks, these two are basically not to be used unless you have profiled your application and found that the lock is a contention point. Otherwise, use techniques from that we have discussed previously. Do not use these two because they will just slow your whole system for no good reason. Versus if you do the fine-grained locking, where you divide, for example, a hash table into buckets, then you'll get more streamlined performance by just doing that. Let me just try to, yeah. So, and last time we started talking about that there is a problem with test and set. And the main problem is that if you look at this code, where you have a counter, the increment function, that uses the test and set atomic function to basically have a lock on on some data structure, which is or on some data, which is in this case the value, and then you basically increment the value plus plus, and lock is free. And then you basically have a memory barrier to make sure that everything before that is implemented with absolutely no out of order execution. That everything before that is implemented before everything that comes after that. And then the problem occurs when many processors try to acquire the lock at the same time, because what would happen is that if you have multiple processors, each processor will have its own cache. And last lecture we talked about how the cache hierarchy looks like in your system. And then using, since you have your own cache, then you will need to synchronize your cache once an operation has happened. So if one thread at core 1 changes the value to from 0 to 1, then another thread at core 3 that is now gets scheduled on core 3 and is trying to increment the same value will actually have a cache miss because the value has been updated, and the thread on core 3 doesn't have the new value, so it will need to flush its cache, it will need to flush its pipeline, and it will need to basically fetch the data from the cache of core 1. And that basically means that you will have a lot of these operations that are actually not needed in any way. And you also might have the case where the value pings between caches. So you have basically thread 3 and thread 4, so a thread on core 3 and a thread on core 4 that are going to run, and then the thread at core 1 is going to run again. And imagine that this value now will need to jump between all three cores and keep pinging. And if you have a 2-core machine, then you will have, for example, core 1 and core 2, and the value will keep pinging between both caches. So this one will incremented by 1, and then the other one incremented by 1. And since one of the threads gets a lock on the value, then the other two threads cannot do anything, and then it will eventually update the counter. So in this case, for example, it's much better to have a single thread running and basically doing the operations. And there was a question last time about why was this performance. If you have one thread running on one array and two threads running on two different arrays, the two threads running on two different arrays will actually, since the two arrays are completely so you divide the arrays from the middle, and then you have the right hand array sort of and the left hand array, if you may say that, and then each thread will operate on these, and there will be no cache misses, because cache I actually reread what happens again, because the cache gets loaded in some defined word size, so 64 kilobytes for example per every cache read, and that's basically trying to also predict what next data you're going to use to. And if you have two threads that run on odd and even, then the odd one will actually run, and then trying to basically optimize the cache will try to fetch new data, and that data will be typically the next 64 kilobytes. But this is not the data that thread is going to use anyway, because that thread is going to use the one after, or will need other data also besides this 64 kilobytes, because this 64 kilobytes does not have to contain all the data for the next odd for the next odd entry in the array. So there are other cases. For example, you can have a case where also you get a problem because a thread on the same processor acquires the lock right after a release. While at the same time, what is happening is that so the thread on the same processor is kind of fast, so it gets the lock, while the other threads are try to get the lock, not knowing that still that the thread on the same processor acquired the lock. So the data will be propagated to the other threads running on the other cores, while it's actually going to need another propagation because already another thread is changing the data. So suppose that it's the I++ incrementing function So if suppose that it's this function, and you have 4 cores, and for each core you have 4 threads. So on core 1, you increment from 0 to 1, and then you basically release the lock, and at the same time all the other threads try to acquire your lock. So if you have 4 threads per core and you have 4 cores, then you have 15 other threads trying to acquire the lock once you release it. But the ones that are faster are typically the ones on your core, because, well, they can reuse the same cache value, while the ones running on the other CPUs, on the other cores, will actually require to fetch the data across the processor. And although this is pretty fast by all human measures, it's pretty slow by all computer measures compared to running on the same core, and that basically means that the other 15 cores, the other 15 threads will acquire the data. They probably share the same cache on the 3 other processors, so you will have the data propagated to the 3 caches, while this is completely useless actually, and you will be blocking the 3 other cores while doing nothing. So and if the critical section is short, so if it's just something like I++, then value++, then what will happen is that you will end up in a situation, in a very weird situation, where you have even the critical section finishing before the data has propagated to the other caches. So this is the curve that we showed last time on how MCS locks perform versus if you just use test and set locks and test and set locks. They're both, I mean, we talked about test and set, but we have not talked about that, but it's pretty well described in the book, and it's not really something that we need to talk about. And as you see that as the number of processors increase, then the time required increases by the other machines. So let's look at some of the approaches. We are sort of reviewing what I said last time, but I think it's worth doing so, because I felt, at least to me, some parts I was just not in the mood on that day. So some approaches: you insert a delay in the spin loop, so that you do not try to access the data, fetch the data from the caches while it's being changed, but rather wait a bit longer until the data gets a bit more stable, or someone else acquires it, and then you will not try to acquire it before. You can try spinning adaptively, and then there's the MCS lock that we will talk about more. So atomic compare swap, we said that this is an atomic processor provided function or procedure that operates on a memory word, that basically checks that the value of the memory word that you are spinning on has not changed from what you expect. So it's basically sort of spin. It's a function that provides you with a way to efficiently spin on just a memory word until someone changes that memory word for you. So the way it's used to actually build MCS locks is that you use it to build a queue of waiting threads, and waiting threads add themselves to the tail of the queue and basically spins on a flag in its queue entry. So it keeps spinning on some word that is designated for it. And of course, I mean, right here I talk about if it has changed, return an error, but then you can always have not in your if function or in your for function or in your while function. So have the exclamation mark basically. Then once the thread adds itself to this tail of the queue, it spins on a flag in its queue entry, and this flag is changed by the other threads in the queue. And it's sort of a first in first out system, as it's mostly used inside the kernel. So what you have is that the thread before you will change that value for you so that you can get out of your loop and basically start working on the new data. So this is basically how an MCS lock is implemented. You maintain a list of threads waiting for that lock, and the front of the list holds the lock. So the first one in the queue holds the lock, and the last one in the thread is the newest one, and it's the last one to run basically. Yeah, you basically have an implementation or a pseudocode that looks like this. The lock is passed setting. So in the TCB, in the thread control block, you have basically a bool need to wait. This is basically the flag that you spin on. And the next, and you have also a TCB next. And once you basically quit, you try to change your next the TCB the bool need to wait in the TCB of the next thread to you. Okay, so and if need to wait is false, then you run. If need to wait is true, then you basically need to block. And this is how the operation would look like. So you'll have in the beginning a tail nil. You'll have nothing in that queue, nothing in that thread, and then thread A joins, and it doesn't have to wait. So need to wait is false. And then thread B joins, and since thread A is still running, then it has to wait. So its true is false, and it actually changes the value in B. In A, the next value to be B, and then C joins, and it has to wait for B now, and so on. And you might even have a very long list of threads, and this is mostly used inside the kernel. The other way to handle kernel locks is to use read copy update. It's this is stuff that you mostly do not use in your day-to-day locking, but it's mostly for very high performance systems, and they're used in the Java virtual machine, for example, in some of the compilers and in the operating system. So more towards the systems programming side rather than the the day-to-day programming. And you can also think of them as something that you will use if you go and work for Google or Facebook or one of the larger companies that have high infrastructures and you're working as a back-end engineer, then yes, this will be also something that you will be looking at. So read, copy, update, we sort of talked about them a bit also last time. And the goal is to have very fast reads to share data, and restricted updates, and the updates are basically, or the writes are slower. You can have multiple concurrent versions of the same data at the same time, well, you need to handle that because what you have is that you have no locks on reading, but you have locks on writing basically, and the locks on writing stops multiple threads to write concurrently, but does not stop other threads to read the old data at the same time. The way it works is that the writer basically takes a copy of the data, operates on it, and then posts a pointer to the new data value somewhere. Somewhere is something that is predefined, of course, and basically in that place all threads can see that now there is a new version of the data that is available. But since some of the data starts the read maybe before you start the write, so let's suppose that you have a write, the one at the bottom that's called write new, that starts while a couple of threads are actually reading. Okay, so you have two threads on top that read and finish before the write even finishes. So they will operate on the new on the old data, while some threads actually start before the new write is completed. And in that case, these threads can end up reading either the old data or the new data, because the new data will be finished at the update is published line. And then if you have the data by then and you're rereading, because the thread might be rereading the same value multiple times, then the thread might end up with multiple versions of the value. And then it's up to the thread to operate on the old or the new value. And well, then you have a grace period for all threads to finish what they are doing with the old value before you completely override the old, and override the old value. Any new thread that starts after the update is published will read the new value only, will not read the old value, because that just doesn't make sense. And then basically you have a grace period after which all old values are flushed. And if you have something that is running for longer, then that will have to update itself. So if you have a thread that runs for longer than the grace period, you should know that, well, you might be subject to reading multiple values at the same time. So you have to handle multiple different value reads. And then when the grace period ends, the delete command is issued to the old value. So the way that read copy update implementation is that readers disable interrupts on entry, and they guaranteed to complete the critical section before the grace period finishes. And there are no read or write locks, basically. And since you're disabling the interrupts, that means that you have to run pretty fast, so that it's used in the kernel. It's not used outside of the kernel for this reason, because you basically disable interrupts. And also one of the reasons that you disable interrupts while reading is that you do not want even more uncertainty by having an interrupt that rewrites some of the values that you are reading, and then it's just a mess of inconsistencies. The writer, on the other hand, needs to actually run, so acquire the lock, compute the new data structure, publish the new version, release the lock for others to write, but still the writer is not done. It needs to wait for the grace period before it's actually done. And then after the grace period, the writer has to delete the old data, and then the writer is now considered done. And you can see here that you can have, this is basically a multi-threaded version with concurrent reads and writes. So you can see that line 1 has 3 reads, line 2 has 2 reads, line 3 has 2 reads, line 4 has write, line 5 has a write, and line 6 has a write. And you see that on the first 2 lines, they run concurrently, actually the first 3. So you acquire read lock, which doesn't mean anything, and you start reading the values concurrently, it's no problem, and you unlock. And here, locking and unlocking is just releasing the releasing the interrupts and acquiring the and stopping the interrupts. Then the write, you have a write that starts, it acquires a write lock, it publishes value 1, and then it has a write unlock, and then it synchronizes. Okay? And the synchronization is basically the cleanup and the garbage collection and so on. On the 5th line, there's a writer that is trying to acquire the write lock. It is not able to acquire the write lock until on line 4 the writer is done. And then you basically have you start publishing version 2 at that point. And on the last line, again, another writer tries to acquire the lock. It's not able to acquire the lock until the write unlock is done, and then a new value is synchronized. So now that we are done with talking about different ways to synchronize multi-threaded and multi-objects applications. So let's look a bit about at deadlocks. You have studied a bit about deadlocks, but let's iterate a bit on what they are, because they are pretty nasty when it comes to the operating system. So it's basically if you have resources that are contended and there's just not enough of them. So any passive thing needed by a thread to do its job is the resource, of course. And a deadlock is basically occurs when you have circular waiting for the resources. Um, so looking at, for example, this example, you have a thread A and thread B. Lock each thread tries to acquire two locks, and thread A acquires lock 1 first, and thread B acquires lock 2 first, and then they basically try to acquire the opposite locks after the first one. This is the pretty simple case, and then you end up in a circular deadlock. But you can have it in a system like this. If you have a bidirectional bounded buffer, for example, so you don't see any threading here, but you just see that buffer 1 tries to put data, and sorry, thread A tries to put data in buffer 1, and retrieve data from buffer 2. But in the beginning, it tries to put two pieces of data in buffer 1. While thread B tries to do the opposite. It tries to put data in buffer 2 and basically get data from buffer 1. If both buffers are full, then basically when buffer 1 starts trying to putting in data when thread A tries to put data in buffer 1, then the thread is full, so it has to block until somebody empties the thread. But then since it's only thread B that can empty the block, and it is now basically also waiting for buffer 2 to empty a bit, then you get a deadlock, although you do not see even a single line that talks about locking over here, because each one of them will wait for the other to empty its bidirectional bounded buffer. It can happen with if you have two conditions and a condition, two locks and a condition variable. So this one acquires thread A tries to acquire lock 1, thread B tries to acquire lock 1, thread A wins. Thread A acquires lock 2, thread B is still locked, it cannot do anything, and basically thread A starts by checking on the condition variable, and it waits on lock 2. Okay, so it basically it has acquired them in the correct order. You have lock 1 dot acquire, lock 2 dot acquire, it already acquired them, but then it needs to wait on a condition variable. While thread B is the only thread that has a signal to break this waiting. Okay, so the condition that signal lock 2 occurs in thread B, but thread B is blocked since both locks are now acquired by thread A. It can happen if you go to India or to Egypt or to Kenya or one of the beautiful countries where people drive with very little laws. You end up in these deadlock situations everywhere, basically. I mean, it's quite common, and then it needs special skills to actually break these deadlocks. You typically have someone going down from the car, signaling to the cars to basically, okay, you stop, you go, and so on until the deadlock is broken. And sometimes people are just stubborn, and you end up in these situations for hours and hours. And I have happily lived in two of these countries that where you need this skill. There's the dining philosophers in the slides I put online. The author of the book called them the dining lawyers. This is the first time I actually use most of his slides because they were good for this section. But he calls them dining lawyers because the author of the book has a bachelor's in philosophy, and he thought that lawyers are just stupid. And well, I happily changed that back to dining philosophers. So you have philosophers sitting around the table trying to eat spaghetti or something, and well, they have chopsticks, and everyone, or a fork and knife, or two forks, or any two pieces of resources that are needed to eat. And if everybody starts by picking the one on his left hand side, then you end up in a situation, if you look at this figure, where there are absolutely no chopsticks empty and no one can eat, and all of them will starve and die. So this is basically a classical problem in computing science, and in having basically the dining philosophers problem. So the necessary conditions for having a deadlock is that you have limited access to resources. If you have infinite resources, then there is just no deadlock. If everybody can acquire the memory, or different memory, or operate in different memory, then there will be no deadlocks. There is no preemption. That is basically nobody breaks the deadlock by its own, because if you have, for example, you can build an algorithm where you basically say that, okay, if I wait on this thread for more than 5 seconds, I'm going to break, which is a valid way to basically break deadlock. And it's actually, I mean, if you look at computer networks, you have the Sysma CD protocol, which basically and Sysma CA protocols, which basically on the Ethernet, and the way, since you have a contended resource also there, you basically have the network line. You cannot really run a lot of packets on the same wire. Just, well, it's electricity, and what you're running is basically plus 5 volts and minus 5 volts, or plus 5 and 0, depends on the signaling, but that's another thing. So if you're sending packets, no one else can send packet on the same wire. And the way that they basically break the deadlock is that they have a collision avoidness algorithm, which basically probes the line, and if the line is contended, if someone is there, then it starts adding a variable random amount of time before it sends, so that since everybody trying to access the line adds a random variable, then you basically end up in a situation where everybody tries to run at a different point in time. Well, there are multiple independent requests that need to wait while holding, and there are circular chains of requests. And the dining philosophers meet the necessary conditions because you have a limited access to resources. You just have to the number of chopsticks is equal to the number of people on the table. There is no preemption. If you take a chopstick away from a lawyer, from a philosopher, then they're no longer in a deadlock. So if they can communicate, and one of them can hand the chopstick to the other, then you basically can break the deadlock. You wait, and they all wait until some resource is available. And you have a circular chain. One left hand, so everyone is waiting to the one on the right-handed, on his right hand to finish, while he's not going to finish. And there are multiple ways to break the deadlock. In this case, one of them would be to add an extra resource, so add just an extra chopstick in the middle of the table, and then only one of them will be able to grab it, right? You can even have the same number of chopsticks, but remove one from the circle and add it to the center of the table. And then, since the rule is that you cannot, you always acquire your left hand side chopstick first, and one of them will not have a chopstick on his left hand side, so he cannot do anything. And then basically the others one of them will acquire eventually two of them. So there are multiple ways to break that locks. these locks. I'm going to sneeze, so I am going to stop. Okay, now I just spared you from hearing my beautiful sneeze. The way to prevent a deadlock is that you can explicit or limit the program behavior, and that's basically trying to set, for example, rules that you acquire resources in some certain order or some. So it's, and if you do not acquire the resources, the first resource, then you cannot acquire the second one, basically. So you can exploit or try to limit the program behavior. You can try to predict the future, so you can, at the beginning of trying to acquire a resource, look at the whole system and see if anybody has some of the resources that you're going to need, and there's a possibility that you'll end up in a deadlock. And the third one is basically to have detection and recovery mechanisms. So you try to roll back a thread, you try to kill a thread, or try to do something on this order. So exploiting or limiting the behavior, of course, one of them is provide enough resources if you can. And one way that, for example, in Android phones and in multiple mobile phones, they fixed that is that when you need some resources, so when you need some memory, for example, and mobiles used to be very memory hungry and very memory limited. Right now you get really large memory sizes, but beforehand you used to really have like 512 kbs of memory with multiple applications trying to run. So the way that mobile phones did it was that to basically never start running anything before allocating the maximum amount of resources that is going to be needed by that application beforehand. If you cannot acquire enough memory, then you're not going to run this application as a mobile. And that was one way to basically make sure that, well, the user will either close other applications that he's not using, or well, the application will just not run. You can eliminate any waits while holding. You basically release locks when calling out of a module. So one example that where we saw a problem was basically the doubly linked buffer, where you were basically trying to put and get, so put data and get data. And one way would be to actually try to always release any lock when calling out of a module. So if you're trying to go to put, for example, you would release all resources that you already are holding, and any locks that you're already holding. And that basically requires a complete restructuring of your program to allow this, because otherwise it just doesn't make sense. And you can eliminate circular waiting by always acquiring locks in a fixed order, so you cannot acquire lock 1 unless you have lock 0, for example. And this is implemented, for example, when you move one file from one directory to another. You basically have the same lock ordering mechanism, so that you do not end up with inconsistencies. So you acquire A, acquire B here, acquire C here, and maybe you will need to wait for B here. If you see this happening, then what you will do is that you will never acquire B here anyway. Yeah, so you try to basically say that if you cannot acquire B without acquiring A, for example, or if you acquire A, then no one can acquire B. You can set such prevention rules. And that basically means that your whole program will be much more complex. So deadlock dynamics, you have 3 states on which any lock can be. First one is the safe state. It's actually for the whole system. That's basically when for any possible sequence of future resource requests, you will get all resources granted, basically. So if you try to acquire any locks, you will always have them. If you try to acquire memory, you will always have it.
And that's the safe state, that's the state of the system, for example, and that state can change by, for example, starting a new application, because when you start a new application, then you're contending between both applications for the memory, for example, they try to expand the memory, and in that case, then you might change the state from safe to unsafe. And an unsafe state is that there exists some sequence of resource requests that can result in a deadlock. And that basically means that, for example, if you're, let's look at the memory example. So if you start Eclipse and run nothing in it, then yeah, it runs. But if you and start Chrome with it and start 100 tabs with it, then yeah, it runs with Eclipse. But then if you start testing your multi-threaded code in Eclipse, clicking run, then you are actually spawning new processes from new threads or processes from within Eclipse, and that basically means that you keep acquiring resources. You might end up in a situation where there is not enough memory for both Eclipse and your Google Chrome with your 100 tabs, and then you end up in a deadlock. And a deadlock is what is called a doom state, and basically that's when all your possible computations lead to a deadlock. And in case of memory, it's pretty clear what you do. You basically kill both applications, or one of them at least, as an operating system. But for locking, it's not really clear. So your program can basically follow a trace from being safe to being unsafe based on something that you call or some run that you run.
So looking back at the dining philosophers, as we said, it meets all the conditions for being in the deadlock, and there are multiple ways to break that deadlock. One of them is basically to have an extra chopstick, for example, in the middle of the table. One of them would be, so if you can add some extra resources, you can change it such that you need to pick two chopsticks at the same time, and if you don't, put down whatever you have picked. You can change it by just moving one of the chopsticks from the left hand side of one of the philosophers and putting it in the middle of the table, and that basically and have still the rule that to pick the left hand side one first, so that philosopher has no longer a left hand side one, and have a rule that if you are not able to pick both sides at the same time, if you don't have two chopsticks, you try to grab the one in the middle. So there are multiple ways to break that deadlock, as we say. There's the communal dining philosopher's problem, and that you have basically instead n chopsticks in the middle of the table, and n philosophers each can take one chopstick at a time. And then you can have, for example, a rule that basically says that I pick a chopstick as long as it is not the last one in the middle. That basically means that if you have n chopsticks and in the middle of the table, and each one picks one, but checks also how many are remaining on the table, and if it's just one, then he leaves it, then that will basically break also your deadlock. And you can reflect on this as different ways to actually implement free locking mechanisms in your system. So communal mutant dining philosophers is that you have n chopsticks at the middle of the table, and philosophers each take one chopstick at a time, but you need k chopsticks to eat, where k is greater than 1, and k can be 3, for example. And then you will basically implement it such that, well, going back to threads, suppose you have n threads that will need each 3 locks or something to proceed. Then you will implement the same mechanism by basically saying that I take one, and I do not take one if the remaining ones is less than k minus 1. So if I need 3 chopsticks to eat, I'll pick one as long as there are more than 2 chopsticks on the table. Okay? Uh, so uh, that way you basically will end up with again a possibility of another uh, another deadlock, which basically is that you might end up in a situation where two philosophers have two chopsticks and one less sufficient, right? But then you add also that I will not pick it if it's less than two also. So if somebody picks if somebody picks one of the two that are remaining, so if everybody picks one as long as there are more than two on the table, okay, and no one and you do not pick the last one unless you have two already, okay. So you cannot end up in a situation where with a deadlock again. There are methods that tries to predict the future, and one of them is Banker's algorithm, which basically tries to state the maximum resources needed in advance. So you as a programmer, you try or you basically make the program try to predict the maximum resources needed in advance, and you allocate resources dynamically when they are needed, and wait when your granting requests lead to a deadlock. So this is different from just blind allocation in the sense that it has an extra optimization layer. So you basically say that, okay, I need this much amount of memory and these three locks and these data, this data to basically proceed from the very beginning. But then you do not get allocated this blindly when you start, but rather you basically start by whenever you start your operations, you set a flag that you're starting, and these are things that you're going to need, and then any future thread that tries to start will check if when it starts it can lead to a deadlock. Uh, yeah, so and requests can be granted if you have a way out of a deadlock, basically. And you grant requests if and only if they result in a safe state, and the sum of the maximum resources needed to current threads can be greater than the total resources. So, so you can proceed basically, and you can proceed even with more resources being allocated in theory to threads than are available, but you still have a way to finish, maybe by blocking some operations. So an example is that you proceed if and only if the total available resources minus the number of allocated is greater than the maximum remaining that might be needed by the new thread that is starting. And that basically guarantees that this thread can finish, although it will have to wait for some of the other threads to finish in the beginning. And this is how it looks like. So you have some initializations of the value of the different variables you check when you're doing the resource the thread scheduling, and that's basically you pick the number of resources, number of threads that are going to run, the available resources, you have them in a list, the maximum usage of resources I needed by any thread. So you basically have an availability matrix for all different resources that are contended. So and that availability can be of one, right? So you can have only one. So if for some of the values, so if you're, for example, doing the value plus the increment code we have been looking at earlier, then your availability of this resource is one because you just have one counter in this case. While in the case of that, if you in the case of this particular case, you have just single variable, but imagine that you have multiple variables that are dependent in some way. So you can have an availability of that resource of one, right? And then you basically for each thread that is entering, you have the Emacs dictionary sort of, or map that basically says, or double array that basically says that the maximum amount of resources I need by thread needed by thread J, and if that resource has just one in availability, then no thread can, for example, require two of it. So you cannot require two of the value parameter in the increment function, right? Because there's just one counter there. And then you basically have an allocation double array or matrix or map or dictionary. I mean, the implementation can differ based on your programming language. And then you basically have code that checks once you get a request, which is the code lower. I mean, the bottom half of the of this slide, which is basically a code that checks when a request arrives if there is enough capacity for this request. And if there's enough capacity, this request is basically a thread. Then it will schedule it. If not, then it will not schedule it. And you start by basically acquiring a lock, checking that it's safe to proceed. If it's not, then you break. And while it is safe, then you basically while it is not safe, you basically block and do nothing. Versus if it's safe, then you basically start allocating the resources, and when you do the allocation, you basically change all the different parameters that you have defined earlier in your class. For example, the allocation map or the allocation array, you basically change the resources allocated to the thread by increasing the number of it, and you decrease it from the available resources, and then you basically again assert that things are safe still, and you release the lock. And then isSafe is basically a function that goes, or a procedure that goes through all the threads that you have, all the resources that you have, and all the available resources that you have, to basically see if there is a possibility of a deadlock. And that is basically by making sure that there will be eventually enough resources for a thread to continue. Otherwise, it will just break, right? And you can see that in doing that, so in doing this check, basically, you try to see if there is enough available resources now or in the future that, for example, the lock is going to be released in the future. And then you have a function that is called would-be-safe that basically checks for if the lock would be safe would be released in the future, so that you can acquire it, or if the resource would be released in the future, so that you can acquire it. And the way it does that is that it hypothetically decreases. It hypothetically simulates the case when you basically remove one of the threads, and checks what would happen to your threaded program, basically, in that case, to if you add the new thread. The final way to manage deadlocks is basically to try and detect and repair. You basically shoot a thread to make sure that it gives up resources if you end up in a deadlock. So you pick a thread that is currently also holding your resource allocation, and you just kill it. Okay, which is the easiest way. And in the Lightning Philosopher's problem, that would be by removing one philosopher, killing him, or doing something that's kind of mean, but that would break the deadlock. So this is not always easy, because with a mutex, for example, you cannot just kill a thread, because everything will be in a non-consistent state. unless you basically have written a very clean exception handling code in your program. So there are also other ways. One of them is basically that you simulate that everything will be fine. I'll just continue and think that nothing will happen. Okay, it's kind of similar to the to the RCU locks, where you basically go on reading and saying that things will happen. Um, it's mostly used, it's or not mostly, but in many cases it is used in large distributed systems to just like, well, get the system outside of this state. This is again not a very wise idea generally, because you might end up, I mean, especially in operating systems, this will basically kill your operating system, because you'll probably end up in, I mean, you defeat the purpose of locks in that case. If you just continue thinking that, oh, there's nothing, there's nothing wrong with me continuing, you will end up with a very unstable operating system. So you don't do that in operating systems. You do that more for operations where you don't really care if what will happen if the state is not consistent. Consistent. The third way is to try to roll back actions of the deadlocked thread. So you basically try to to remove the thread, and so if a thread has acquired some resources in some sequence, then you start releasing the resources in an opposite sequence, so that you until the deadlock is broken basically, and then maybe lock on. So for example, if you're locking A B and the other one is locking B A, then you basically are you'll be waiting for lock B to get released. So you basically will roll back. So you have not been able to lock A anyway, because lock A was acquired, so you just roll back from lock B, and that should be it. And that would require your system to actually know a bit of its history. And this is actually used in database systems, and it's easy in database systems to do that. Not very easy, but easier than in operating systems. And the way that the algorithms for this work is that they scan for graphs. So you scan basically your system to try to detect cycles in your system. And in that case, you basically can try to break your cycle. These are basically the ways that you would use to detect and repair a deadlock. Now that we have been talking about deadlocks, it's actually worth saying something about a radically different approach that has been proposed in between researchers and programmers in writing concurrent programming, and that's basically by writing code that completely doesn't have locking at all, with non-blocking synchronization basically. And their goal is that they wanted to have data structures that can be read and modified without acquiring a lock, and thus there will be never lock contention and no deadlocks. The general method is using compare and swap, which we have talked about a bit earlier, and since basically, as we said, you can have the a thread waiting using compare and swap, waiting for example, for something to happen, for someone to change a bit in the in some memory location that the thread is consistently spying on her, monitoring basically. Okay, so that's a radically different approach to actually eliminate locks and deadlocks. There are a few libraries that have been implemented that way, but they're it's not an easy programming endeavor. It's something actually quite hard to get right, but it's actually worth looking at. So that was just a side note. But for deadlocks, you typically have resource X that is acquired by thread 0 that is waiting for resource Y that is owned by thread 1. Or you might have a multiple threads owning the same resource, because you might have multiple versions or multiple instances of the same resource, and then that would look like that. And the algorithm to break such a deadlock is very similar to the banker's algorithm we talked about, and it has is deadlock. Is the name of the function, and it is actually quite similar to the is safe algorithm in the banker algorithm. And what it tries to do is that it tries to check if you already have a deadlock by looking at the resources that are acquired and the resources that you're waiting for. So if you're in need of a resource that has 0 and another thread is waiting for a resource that you have and thus have 0, then you're in a deadlock. And that's basically how it works. So it's a simple modified version of the banker algorithm is safe. And as we have talked about the bounded buffer example with put and get, it's worth noting that this is an implementation of a basically thread of a safe lock-free bounded buffer, a thread-safe lock-free bounded buffer. Yeah, the implementation is pretty straightforward. You do a consistent copy and you work on the copy instead of working on the actual value. With this, I conclude this part of the lecture. I will see you tomorrow. We'll cover some of the issues. We'll have some questions and some answers. And as I said, I will update you very soon on the deadline, the new deadline for assignment 2. In reality, you can actually do assignment 2 right now, but I would rather postpone the deadline for a while. So see you tomorrow.